Hi students, in this class we discuss one topic in NMR spectroscopy. The topic is shielding and deshielding effects. This is the very important topic in NMR spectroscopy. You all know about the what is the NMR and what is the principle of NMR and what is the chemical shift. That means the position of the NMR signals can be expressed in terms of chemical shift. It is very important parameter in NMR spectroscopy. In some compounds, the chemical shift value is different from the expected. Why this happen? That can be explained with the help of shielding and deshielding effect. Okay, in class I can express the topic. What is shielding effect? What is shielding effect? Shielding effect is also called the upfield effect. Upfield effect. What is the shielding? When our protons in the compound are placed in the external magnetic field, that protons are aligned in the two states, that is alpha and beta state. There is the energy gap between these two states, and when radio frequency radiation is incident in that compound, the protons are undergoes the resonance that causes the NMR spectroscopy. You know that. In the same time, at the same time, when place the compound in the external magnetic field, the electrons neighbor to the protons are affected by the external magnetic field. External magnetic field. That means the electrons are causes to circulate and they gives the secondary magnetic field. That means the electrons produces the secondary magnetic field around the protons. When proton is placed in the external magnetic field, the neighboring electrons are causes the secondary magnetic field, This secondary magnetic field can changes the chemical shift value, When the protons are placed in the external magnetic field, the electrons causes the secondary magnetic field around this proton. This secondary magnetic field can be opposes the our external magnetic field or reinforce the external magnetic field. When suppose the external magnetic field, that is the secondary magnetic field, induced magnetic field caused by the electrons is opposes the our applied magnetic field, then that protons called shielded protons. When electrons create the secondary magnetic field around this proton, and this is the opposes induced magnetic field opposes the our external magnetic field. This time the proton experiences the less magnetic field by the external magnetic field, so that to get the resonance, you must increase the our external magnetic field. So it is called the upper field effect. Okay. This secondary magnetic field caused by the electrons is opposes the external magnetic field. Then that proton feels less magnetic field by the external magnetic field, so that this proton is called the shielded proton. This effect is called the shielding effect, so that this shielded efficiency can be removed by increasing the external magnetic field. So this that means NMR absorption can be occur at high field. So it is called the upper field effect. So it can be easily shown this diagram. Generally, the normal proton having this energy. Okay. For normal protons, you require this energy. This without any induced magnetic field, the protons required. This is the energy for the resonance. But in case of the shielded protons, the induced magnetic field opposes the external magnetic field. The protons feels the less magnetic field. That amount of magnetic field can be supplied by the externally. So this gap can be increased by this due to the shielding effect. So it feels very low of external magnetic field that can be supplied by our external magnetic field. So this is called the induced field effect. This is the applied field effect. The totally the required field is increased this amount. So this is called these protons are called the shielded protons, and this effect is called the shielding effect. The example for the shielding effect is the acetylene proton. This is the best example. You know the acetylene C2H2, and the carbon has the triple bond, and this carbon has the terminal hydrogen, this carbon has the one hydrogen. Okay, and when acetylene is placed in the external magnetic field, this acetylene is placed in the external magnetic field. Okay, these protons surrounded by the acetylene electrons in the acetylene, the electrons creates the induced magnetic field. Here electrons creates the external induced magnetic field. This induced magnetic field has the direction. This is the direction. Okay, here this proton, the electrons causes the induced magnetic field. This is the direction of the induced magnetic field. Okay, here the induced magnetic field direction has, this is the direction. Here you can apply the magnetic field here. This is the direction, So these two fields, that is induced field, secondary magnetic field due to electrons is opposes our external magnetic field. This induced magnetic field protects shields the proton. So this proton is called the shielded proton, and this effect is called the shielding effect. To continue the resonance in the NMR, you can increase the external magnetic field to get the resonance. So this is the shielding effect. The second effect is the deshielding effect. This deshielding effect is also known as the downfield effect. Here the protons, the one proton is there here, it has the spin. For example, proton, it has the spin. The proton surrounded by some electrons. These some electrons are creates the induced magnetic field. Okay, this induced magnetic field is reinforced. That means parallel to the external magnetic field. This is the direction, induced magnetic field direction, and this is the direction of the external magnetic field. That means our external magnetic field as well as induced magnetic field due to electrons are having the same direction. Here these protons are unshielded or deshielded. That means the total amount of field effect from external magnetic field and induced magnetic field, this proton feels more magnetic field, so that you can decrease the external magnetic field to get the resonance in the NMR spectroscopy. Here that can be shown in the example very easily. This is the normal protons without any deshielding effect protons. It requires this is the energy, applied magnetic field. Okay, this is it. While protons feels the deshielding, that means the external magnetic field is parallel to the induced magnetic field is parallel to the external magnetic field. The proton feels more fielding by the external and as well as induced, so that you can decrease or downfield the external magnetic field. So that it is called the deshielding effect, and this proton is called the deshielded proton. This is an example, best example of acetylene protons, aldehyde protons, aldehyde or any aldehyde protons. Aldehyde protons are the best example for the deshielding effect. Here, in the aldehyde, you have the carbonyl oxygen, C double bond O, and for one alkyl group, one hydrogen. Okay. Here, this aldehyde proton has surrounded by here electrons. These electrons create the secondary magnetic field. This secondary magnetic field, induced magnetic field, IFE, has the direction like that. This is the direction. This is the direction. In this direction, the protons, the induced magnetic field direction has this direction. Induced magnetic, applied magnetic field also has this direction. These two directions are parallel. That means the same direction. So this protons feels much more magnetic field. So NMR absorption occur at lower field. That means NMR resonance can be observed at a lower frequency of radio waves. So that this proton is called the deshielded proton, and this effect is called the deshielding effect. The absorption occur at a lower frequency, so it is also called the downfield effect. Okay, this is a very important topic. Thank you.